We physicists have held up 100 years, beginning around 1916, for this photograph. It is a region where black holes might just be one of the most captivating and clandestine phenomena known to mankind. They are gigantic beasts in terms of power but are essentially invisible to us. A black hole, for example, measuring 2 to 10 times the mass of the Sun, could be one of these. Thanks to the research conducted over the past decades, we have gone from knowing almost nothing about them to progressively understanding more. Recently, things have become even more intriguing. Kaku has proclaimed that we have finally managed to look at the inside of a black hole. This new information sheds light on nuances that the scientific community might have missed from the very beginning. Join us as we dive further into black holes and uncover what's inside. Space is vast, but what are black holes? Before we dive into the specifics of what Kaku uncovered, we need to examine the basics. While most of us have some idea of what black holes are, there are still gaps in our understanding. In 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the idea was entirely theoretical. It took another 50 years for scientists to find evidence of their existence, which happened during the 1960s. Researchers studying the Cygnus constellation observed an unusually bright blue star emitting X-rays. This star wasn't old. It was orbiting a massive dark object. Upon further investigation, it was revealed that the X-rays were being sucked into this object. Thus, the term black hole was coined. This discovery was crucial because it showed that black holes weren't just a product of Einstein's imagination but a real phenomenon in space that required study. Scientists across the globe began focusing on this black hole, named Cygnus X1, located in the Cygnus constellation around 6,000 light-years from Earth. It was 10 times brighter than the Sun and incredibly dense, with such a strong gravitational pull that not even light could escape it. Hence, it is known as a black hole. The concept of a black hole is both fascinating and terrifying, a region of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole is pulled into it, never to be seen again. This danger makes it essential to learn everything we can about them. After the discovery of Cygnus X1, scientists began searching for other black holes and found that there might be more than 100 million black holes in the Milky Way alone. Because they are so incredibly difficult to detect, we still don't have an exact number. Nonetheless, it seems there are millions of black holes in our universe, making them even more critical to study. The primary characteristic of black holes is their gravity. Their gravitational force is so intense that anything entering them is compressed to an extreme degree, eventually becoming a singularity. In simpler terms, black holes are like giant vacuum cleaners, sucking in everything. One of the most terrifying aspects of black hole research is that if someone were to fall into one, they would be stretched into a single line, a process called spaghettification. This would happen slowly, and the individual would die long before reaching the singularity. In short, no one should ever step into one. However, given how widespread black holes are, could we ever be in danger? Despite the nearest black hole being 500 light-years away, it is still close enough to raise questions. In 2021, scientists managed to produce the first clear photograph of a black hole, specifically the M87 black hole. This black hole was captured over several nights, and with every image, researchers gathered more data. They stitched these individual photos together to create a complete picture, revealing that black holes have 3 distinct layers. It's not just one single, gaping void, as many people assume. The process involves moving through the first 2 layers before reaching the central void. The first layer is called the event horizon. Once you pass this point, there is no turning back. You will be pulled into the black hole. The second layer is the photon sphere, where light circles the black hole. Any light entering this region is trapped and unable to escape the gravitational pull of the black hole. Finally, there's the third layer, the singularity. This is where everything that enters the black hole is compressed into a single point in spacetime, where the laws of physics as we know them break down. At this point, we cannot predict what happens next. The density at the singularity is unimaginable, and physics as we understand it ceases to exist. To make matters more complex, every black hole studied so far is unique. While they tend to follow the same three-layer structure, the way they function can differ significantly. Typically, studying such singularities would involve using telescopes to observe them extensively. However, with black holes, this isn't possible. Scientists study black holes indirectly by observing the radiation they emit and the gas and dust surrounding them. Sending a probe like Voyager into a black hole is impossible, as anything that crosses the event horizon is pulled into the singularity and compressed into nothingness. As a result, spending billions of dollars on probes for this purpose would be futile. Scientists are left with no choice but to study these phenomena in a two-dimensional manner, even though black holes are three-dimensional entities. To complicate matters further, every black hole is unique, and the laws of physics break down inside them. This means conventional scientific methods don't apply to black hole research. However, researchers haven't been idle. There are numerous theories and explanations about black holes. One compelling theory is that they are formed from collapsing stars. When a star exhausts its fuel, it can no longer generate enough energy to counteract gravity, causing it to collapse in on itself and potentially become a singularity. To better understand black holes, NASA scientists directed their focus to the center of the galaxy M87. Astronomers observed a disk of extremely hot hydrogen gas spinning at an incredible speed of 1.2 million miles per hour. The sheer force of the spinning gas should have torn the disk apart, but it didn't. Scientists concluded that a massive object at the galaxy's center prevented this from happening, a colossal mass weighing as much as 2 to 3 billion suns. This object could only be a black hole. However, that wasn't the only theory. In 1963, New Zealand mathematician Roy Kerr used Einstein's equations to propose a new model of black holes, now known as Kerr black holes. These rotating black holes differ from the simple, non-rotating ones initially theorized. Kerr's equations suggested that the rotation of these black holes creates a region of space around them called the ergosphere, where space-time is dragged along with the black hole's spin. This concept added new layers of complexity to our understanding of black holes. In addition to rotation, black holes can also vary in size. Scientists have categorized black holes into three main types: stellar mass black holes, supermassive black holes, and intermediate mass black holes. Stellar mass black holes like Cygnus X1 form when a star collapses. Supermassive black holes, such as the one at the center of the Milky Way, Sagittarius A*, are millions to billions of times the mass of the Sun and are believed to form through the merging of smaller black holes or the accretion of vast amounts of matter over time. Intermediate mass black holes, which are harder to detect, fall between these two categories and are thought to form in dense star clusters. Despite the progress made in understanding black holes, many questions remain unanswered. For instance, what happens to information that falls into a black hole? This question lies at the heart of the black hole information paradox, a problem that has puzzled scientists for decades. According to classical physics, any information that crosses the event horizon is lost forever. However, quantum mechanics suggests that information cannot be destroyed, leading to a fundamental conflict between these two pillars of modern science. To resolve this paradox, physicists like Stephen Hawking proposed that black holes might emit radiation, now known as Hawking radiation, which could allow them to slowly lose mass and eventually evaporate. If this is true, it raises even more questions about what happens to the information during this process. Does it escape as radiation, or is it irretrievably lost? This ongoing debate has sparked a flurry of research and theoretical models, but a definitive answer has yet to be found. One of the most exciting aspects of modern black hole research is the use of cutting-edge technology, such as the Event Horizon Telescope, EHT. This global network of radio telescopes was responsible for capturing the first-ever image of a black hole in 2019, the M87 black hole. By combining data from observatories around the world, scientists were able to create a virtual Earth-sized telescope, enabling them to achieve the resolution needed to photograph the event horizon. This breakthrough provided direct visual evidence of the existence of black holes and opened up new possibilities for exploring these enigmatic objects. Looking ahead, scientists are eager to uncover more about black holes, including their role in shaping galaxies and their potential as gateways to other dimensions or even time travel. While these ideas remain speculative, they highlight the profound impact black holes have on our understanding of the universe. As technology advances, we may one day unlock the secrets of these mysterious entities and gain a deeper insight into the fabric of spacetime itself. For now, black holes remain one of the most fascinating and mysterious phenomena in the cosmos, challenging our understanding of physics and pushing the boundaries of human knowledge. Conditions portray a transforming dim opening, suggesting that it wouldn't collapse into a point yet perhaps form a ring of fire or a slight circle. This turning plate of matter, called the ergosphere, is the area enveloping the dark opening where the laws of physics begin to separate. Kerr's condition also predicted the presence of an Einstein-Rosen bridge or wormhole, a speculative passage through spacetime that connects two separate areas of the universe or even two parallel universes. If one were to fall into a dark opening, rather than being crushed, they might be sucked down a passage through the ring of fire and ejected out of a white opening in a parallel universe. To understand how this works, consider the nature of spacetime in Einstein's theory. Existence is interconnected, forming a four-dimensional surface called spacetime. Objects with mass distort this fabric, creating a gravitational field that causes other objects to move toward them. Imagine a piece of paper representing spacetime. If you place two dots on the paper and define a line between them, it represents how objects travel through spacetime. If you could fold the paper in half to create a shortcut between the 2 points, this represents a wormhole, a shortcut through spacetime that connects two distant points instantly. Wormholes aren't just a sci-fi concept. They are a prediction of general relativity, but no one has observed one directly. Wormholes are inherently unstable and would collapse rapidly. The presence of an Einstein-Rosen bridge would mean that black holes are not just vacuum cleaners but could also be gateways to other regions of spacetime. Could we eventually use a wormhole to travel through spacetime? Unfortunately, the answer is likely no. Not yet. Even if we could stabilize a wormhole, it is unlikely we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit for how fast anything can move through spacetime. Nonetheless, the idea of wormholes and black holes as pathways to other parts of the universe or different times has fascinated physicists for decades. The possibility of shortcuts through spacetime, allowing travel across vast distances or into the past, could be revolutionary, if feasible. The Kerr wormhole, named after Roy Kerr, is one of the most intriguing ideas in this field. A hypothetical passage through spacetime that might connect two distant points like different universes or different times within the same universe. The Kerr wormhole is ring-shaped, like the mirror in Alice in Wonderland, where passing through it could potentially transport a traveler to another universe or time with different physical laws. While the possibility of wormholes as methods for interstellar or time travel is exciting, it is also highly speculative. Some physicists argue that wormholes, particularly Kerr wormholes, might be fragile or impossible to traverse due to extreme radiation and subatomic forces. Critics point out that Einstein's equations used to describe wormholes and black holes only account for gravity and not the quantum forces governing radiation and subatomic particles. To truly understand wormholes, a new theory is needed that unites gravity with quantum mechanics, a theory of everything. Michio Kaku, a renowned theoretical physicist, has been working on a theory of everything for decades. The most promising candidate is string theory, which unifies gravity and quantum mechanics. It proposes that subatomic particles are tiny vibrating strings and that the universe is a symphony of these strings. Just as different musical notes correspond to vibrations of a violin string, different particles in nature correspond to different vibrations of a superstring. String theory also explains many strange phenomena, showing that as strings move through time, they curve the fabric of space, creating black holes, wormholes, and other extraordinary solutions to Einstein's equations. However, the extra dimensions of spacetime predicted by string theory are so small that we cannot study them directly. Even the most precise experiments in our laboratories only use the 4 dimensions we are familiar with: length, width, depth, and time. How can we confirm the existence of these extra dimensions? One possibility is that these dimensions are compactified, so tightly curled that they are invisible to us, like a sheet of paper rolled into a cylinder. If you were an ant walking on the paper, you couldn't see the curve. Similarly, The extra dimensions of spacetime in string theory might be curled into tiny circles or spirals that are imperceptible but influence the behavior of strings vibrating within them. Another possibility is that these extra dimensions were more apparent at the universe's birth, during the Big Bang. According to some interpretations of string theory, the universe began as a 10-dimensional spacetime with all dimensions equally visible. As the universe expanded and cooled, the extra dimensions began to fold up, leaving us with the 4 dimensions we observe today. If this is correct, we might detect traces of the extra dimensions around us. The mathematics of string theory is extremely complex and has opened new areas of research. However, solving the problem of a quantum black hole has proven challenging. While many physicists have attempted, none have yet succeeded. Edward Witten of the Institute for Advanced Study at Princeton has called string theory 21st century physics that fell accidentally into the 20th century. Last year, some physicists announced a significant breakthrough. String theory could solve the problem of a quantum black hole, but only in 2 dimensions, not 10. Many believe it is only a matter of time before someone solves this problem. Until then, it's too early to expect intergalactic or time travel attempts. One thing is certain. There are far too many questions and even more possible answers. Michio Kaku's string theory adds another twist. Perhaps the Big Bang wasn't as big as commonly thought. It wasn't a massive explosion or loud bang, as one might imagine. The theory of the primordial cosmic explosion doesn't explain what caused the bang or how it happened. It simply states that it did. We need a theory that explains what happened before the Big Bang. String theory suggests that our universe might have formed from the collision of 2 separate universes or emerged from another universe, like a child being born from its mother. This connection between universes is known as a wormhole, comparable to a tube connecting 2 bubbles. We may have already found evidence of this umbilical cord linking our universe to another. In a sense, we could be living inside a black hole, unable to perceive it because we exist in 4 dimensions and cannot see beyond them. It's possible that we are in a black hole and that the black holes we study are wormholes to other dimensions.